Throughout history, humanity has been captivated by the significance and influence of the sun. In our pursuit to unravel the mysteries surrounding this celestial giant, we have undertaken numerous journeys to explore its secrets.
NASA's daring plan to visit our nearest star, the Sun, took a giant leap today.
On August 12, 2018, NASA launched the Parker Solar Probe to observe the Sun's outer corona. But things took an unexpected turn. Since its launch, the Parker Solar Probe has made unprecedented discoveries, tasking scientists with more questions than answers. And recently, the Sun just sent us some horrifying messages. Discovery from the Sun. On the mission to explore the Sun, NASA's Parker Solar Probe made history in 2021 by flying through the Sun's outer atmosphere, called the corona. Despite facing intense heat and radiation, the probe still gives us new insights into our closest star. Recently, it identified 18 sun-grazer comets, including 2 non-group comets. This is not the first time that the probe has observed something shocking. In 2018, the probe observed something called magnetic switchbacks, where the Sun's magnetic field suddenly flips. The Ulysses first spotted these. Later in 2019, the Parker Solar Probe shared its early findings, revealing the Sun's magnetic field strength and direction. It pointed out quick changes in the field, hinting that Alfvén waves might help explain why the Sun's outer layer is so hot. The probe found around 1,000 rogue magnetic waves, causing rapid changes in solar winds and occasional flips in the local magnetic field. By studying electrons along these fields, researchers saw that these flips are often linked to faster plasma movement away from the Sun's center. They also noticed an unexpected sideways speed from the Sun's rotation, pushing plasma away from the corona. The probe also discovered a dust-free zone around 3.5 million miles from the Sun, where cosmic dust particles vanish due to solar radiation. During its 8th pass by the Sun in 2021, the Parker Solar Probe encountered specific magnetic and particle conditions, symbolizing its closest approach to the Sun, which NASA called touching the Sun. In 2022, the probe spotted its first comet, PSP-001, during its 12th approach to the Sun. Mission to the Sun. Launched on August 12, 2018, at 7:31 UTC, the Parker Solar Probe worked well after takeoff. In its first week in space, it put out important parts like the high-gain antenna, magnetometer boom, and electric field antennas. On August 20, 2018, the spacecraft made its first planned move in its path, which was 8.8 million kilometers away from Earth, zooming at 63,569 kilometers per hour. They turned on and tested the instruments in early September 2018. On September 9, 2018, the 2 WISPR telescopic cameras had a successful first light test, sending back wide-angle sky pictures towards the galactic center. The probe finished its first Venus flyby on October 3, 2018, getting within about 2,400 kilometers of Venus to slow down and reach a closer orbit around the Sun. The second Venus flyby happened on December 26, 2019, making the probe's speed drop from 2.9 kilometers per second to 26 kilometers per second, and that changed its orbit to get even closer to the Sun. In each orbit around the Sun, there's a science phase where the probe observes independently. During this phase, communication is much less, lasting a few days before and after each time the probe gets closest to the Sun. This phase gets shorter, going from 11.6 days for the first closest point to 9.6 days for the last closest point. A big part of the orbit involves sending data from the science phase, but sometimes it's tricky because the heat shield faces the Sun and there might be interference from the Sun's radiation. After the first Venus flyby, the probe started going in an oval-shaped orbit with a 150-day cycle. More flybys and meetings with Venus made the orbit cycle shorter, leading to the current path. More Venus flybys in the future are expected to keep changing the probe's orbit. The timeline shows important events, like when the probe gets closest to the Sun, flybys, and changes in its orbit. up until the expected events in 2026. The Parker Solar Probe. The Parker Solar Probe marks a significant milestone as it ventures into the low solar corona, a feat never before accomplished by any spacecraft. Its mission revolves around scrutinizing the sun's corona, delving into the intricacies of its plasma and magnetic field dynamics, understanding the energy processes responsible for heating the solar corona, driving the solar wind, and unraveling the mechanisms propelling energetic particles. The spacecraft employs a formidable solar shield to brave the extreme conditions near the sun. At its closest point to the sun, the probe faces an intense solar radiation of approximately 650 kilowatts per square meter, a staggering 475 times the intensity experienced in Earth's orbit. The hexagonal solar shield is a technological marvel, measuring 2.3 meters in diameter and situated on the sun-facing side of the spacecraft. Its thickness of 11.4 centimeters comprises 2 panels of reinforced carbon-carbon composite housing, a lightweight, 4.5-inch thick carbon foam core. This innovative design enables the shield to withstand temperatures as high as 1,370 degrees Celsius. Remarkably, the shield, weighing a mere 73 kilograms, maintains the spacecraft's instruments at a relatively comfortable 29 degrees Celsius. A crucial feature of the shield is its white reflective alumina surface layer, strategically designed to minimize absorption. The spacecraft's vital systems and scientific instruments find refuge in the shield's central portion, where direct solar radiation is blocked. Without this protective barrier, the probe would succumb to damage within seconds. Given the 8-minute communication delay with Earth, the Parker Solar Probe must operate autonomously and swiftly to safeguard itself. The utilization of 4 light sensors to detect the earliest traces of direct sunlight, combined with responsive movements from reaction wheels to reposition the spacecraft within the shadow, underscores the autonomous nature of this groundbreaking mission. As project scientist Nikki Fox describes, the Parker Solar Probe as the most autonomous spacecraft that has ever flown. Powering this ambitious mission is a dual solar panel system, primarily reliant on photovoltaic arrays. A sizable primary photovoltaic array, deployed for mission phases outside 0.25 astronomical units, is cleverly retracted behind the shadow shield during close approaches to the sun. In contrast, a more compact secondary array takes charge during the closest approach, utilizing pumped fluid cooling to maintain optimal operating temperatures for the solar panels and instrumentation. This intricate power system ensures the Parker Solar Probe remains operational and resilient throughout its groundbreaking journey into the heart of our solar system's star. The Parker Solar Probe represents the pioneering spacecraft to venture into the inner regions of the solar corona. Its mission involves examining the structure and dynamics of the sun's coronal plasma and magnetic field, understanding the energy processes heating the solar corona and propelling the solar wind, and investigating the mechanisms accelerating energetic particles. A solar shield is employed to shield the spacecraft's systems from the intense heat and radiation near the sun. This shield, positioned on the sun-facing side of the spacecraft, is hexagonal, 2.3 meters in diameter, and 11.4 centimeters thick. Comprising 2 panels of reinforced carbon-carbon composite with a lightweight 4.5-inch thick carbon foam core, it is designed to endure temperatures of approximately 1,370 degrees Celsius. Weighing a mere 73 kilograms, the shield effectively maintains the spacecraft's instruments at 29 degrees Celsius. The shield's reflective alumina surface layer minimizes heat absorption. The spacecraft's systems and scientific instruments are strategically located within the shield's central shadowed region, fully protected from direct solar radiation. The probe would quickly sustain damage without this shield and become inoperative within seconds due to the intense solar conditions. Given the approximately 8-minute round-trip radio communication delay with Earth, The Parker Solar Probe relies on autonomy for swift self-protection. This involves 4 light sensors, detecting the initial signs of direct sunlight, reaching the shield's limits, and triggering movements from reaction wheels to reposition the spacecraft within the shadow swiftly. According to project scientist Nikki Fox, the team characterizes it as the most autonomous spacecraft that has ever flown. The primary power source for the mission is a dual system of solar panels. A primary array, utilized for mission segments beyond 0.25 astronomical units, is retracted behind the shadow shield during close approaches to the Sun. Meanwhile, a smaller secondary array powers the spacecraft during the closest approach, employing pumped fluid cooling to maintain the operating temperature of the solar panels and instrumentation. The Parker Solar Probe is equipped with 4 primary instruments, which are: the FIELDS captures the scale and configuration of electric and magnetic fields in the Sun's atmosphere. FIELDS measures waves and turbulence in the inner heliosphere with high-time resolution, providing insights into the fields associated with waves, shocks, and magnetic reconnection. The instrument uses 5 antennas to measure the electric field around the spacecraft, with 4 extending beyond the heat shield into sunlight, enduring temperatures of 1,370 degrees Celsius. The antennas, made of a niobium alloy, operate in 2 modes to measure the properties of the fast and slow solar wind. Additionally, 3 magnetometers assess the magnetic field, including a search coil magnetometer for measuring temporal changes and 2 fluxgate magnetometers for gauging the large-scale coronal magnetic field. Stuart Bale is the principal investigator at the University of California, Berkeley. The second instrument is the ISOIS, which utilizes 2 complementary instruments, EPI low and EPI high. ISOIS measures particles across a broad energy spectrum. By examining electrons, protons, and ions, ISOIS aims to understand the life cycle of these particles, including their origin, acceleration, and movement from the Sun through interplanetary space. EPI low distinguishes carbon, oxygen, neon, magnesium, silicon, iron, and helium isotopes. EPI high, designed with 3 particle sensors, measures higher energy particles and identifies charged particles through ionization. David McComas is the principal investigator at Princeton University. Third is the Wide Field Imager for Solar Probe, an optical instrument that employs 2 cameras with radiation-hardened active pixel sensor, CMOS detectors, to capture corona and inner heliosphere images. The lenses are made of radiation-hard BK7 glass, suitable for space telescopes. Russell Howard at the Naval Research Laboratory is the principal investigator. Lastly, the SWEAP counts electrons, protons, and helium ions, measuring their velocity, density, and temperature properties. The Solar Probe analyzers and the Solar Probe cup constitute the main instruments. SPC, a Faraday cup, catches charged particles in a vacuum and, exposed to the Sun's full light, heat, and energy, determines their properties. SPAN, consisting of SPAN A and SPAN B, uses wide fields of view to observe areas not covered by SPC. Justin Casper at the University of Michigan and the Smithsonian Astrophysical Observatory is the principal investigator. Additionally, a theoretical investigation named Heliospheric Origins with Solar Probe Plus provides theoretical input and independent assessment of scientific performance. Marco Velli at the University of California, Los Angeles, and the Jet Propulsion Laboratory serves as the mission's principal investigator and observatory scientist, extending from 2010 to 2024. Parker Solar Probe's trajectory. The mission design of the Parker Solar Probe involves utilizing repeated gravity assists at Venus to gradually reduce its orbital perihelion, aiming for a final altitude above the solar surface of approximately 8.5 solar radii, equivalent to about 6 million kilometers. Over nearly 7 years, the spacecraft will undergo 7 Venus flybys to incrementally contract its elliptical orbit around the Sun, completing 24 orbits. Given the predicted adverse effects of the near-Sun radiation environment, including spacecraft charging, radiation damage, and communication disruptions, the orbit will be highly elliptical, minimizing the time spent near the Sun. The trajectory demands considerable launch energy, prompting a Delta IV heavy-class launch vehicle and an upper stage utilizing the Star 48 BV solid rocket motor. Interplanetary gravity assists will contribute to further deceleration relative to its heliocentric orbit, establishing a heliocentric speed record at perihelion. As the probe circumnavigates the Sun, it is anticipated to reach up to 200 km per second, momentarily securing its status as the fastest human-made object, nearly 3 times faster than the previous record holder, Helios 2. On September 27, 2023, the spacecraft achieved a velocity of 176.5 kilometers per second, enabling it to cover the distance from New York to Tokyo in just over a minute. Like any object in orbit, the spacecraft will experience acceleration as it approaches perihelion, followed by deceleration until it reaches its aphelion due to gravitational influences. Do you think this exploration would help us understand the Sun better or show us more puzzles? Let's hear from you in the comment section. Also, like this video and subscribe to this channel for more.